So today I'm going to go over how to work an MTMM, so multitrait-multimethod model in lavaan. And we're going to do what are traditionally known as the Widaman Steps. And this doesn't always work, so one of the big criticisms, especially if you've been reading maybe the Brown confirmatory factor analysis books, is that it doesn't always run. And so it has a bad tendency of giving you a Haywood case in the first step. If you can get it to run, however, it is a great way to test a multitrait-multimethod model. But no, if you can't get it to run, I'd really suggest reading the Brown book about correlated uniqueness models, or there's some newer books that talk about Bayesian interpretations for models. And so I'm going to go over the traditional steps in this video, but with the warning that often tends to have some trouble converging. And we'll see a little bit of that here, but that's more of the data set that I'm using than the particular model that I'm running. Okay. So what we're going to do in this assignment is program an MTMM in 4 steps, talk about the fit indices, the loadings, and an interpretation of what happened in that analysis. Okay. So I'm going to use meaning and purpose because I work with some people who are in the logotherapy field, and I'm their resident math nerd. And so I help them look at their scales to determine their divergent and convergent validity. And so one of the big things going on in that field is lots of names for what we consider the same thing. So there's meaning, there's purpose, there's resiliency, there's hardiness. And so this is a really good way to test if traits are actually separate things, and to test if the methods are measuring those traits and if the methods are still useful. So we have 3 scales here. We have the Meaning in Life questionnaire, the Seeking of Noetic Goals questionnaire, and the Purpose in Life scale. And I'm going to take just a couple questions from each of those and test the divergent and convergent validity of traits, and then the usefulness of the methods. Okay, so we're going to have traits and methods in the same model. And then we'll test 4 different models: correlated traits and correlated methods, a model with no traits and correlated methods, a model that's perfectly correlated traits, indicating that the traits are exactly the same thing, and correlated methods, and then correlated traits and uncorrelated methods. So we're going to compare each of these models to model 1, because model 1 is considered like the best case scenario, where traits and methods are correlated but not perfectly, and the items are loading on what you'd expect them to load on. So we're going to talk about convergent validity, discriminant validity, and a second type of discriminant validity. So this really should say convergent validity of the traits here as well. Okay, so the first 2 are traits, the second one's methods. And then we'll talk about how can I interpret the loadings. So if you're going to do a correlated uniqueness kind of scale, you would probably look more at the loadings and not scale, a correlated uniqueness type of model. You would look at the correlations out here. And then we'll look at some more divergent validity issues. Okay. So let's start by programming just a traits CFA and just a methods CFA, because you expect models to, those questions to load on their specific latent variables. And if they don't, if your CFA, but at least the traits doesn't work, MTMM is not appropriate. Okay. So we're going to start by programming just traits and just methods, and I think that'll help us move on to the other models. So I got Studio open here, and as always, first thing you want to do is load the libraries. So we're going to use lavaan and semPlot to make some pictures for us. There is an MTMM option in the psych package, I believe, but it does the correlation table type analysis, and this is a structural equation modeling class, so we're going to do it in a different style, but there are many ways to do MTMM, just a warning. Okay. So let's load the data, and I have found from playing with this in lavaan that it works much better if you have the real data. I had a lot of trouble with running this from correlation tables. So import data set from text file. And I have the data. We use this as a class example too, so we're going to do this data. I'm just going to call this data. And I'm going to use the header option, because remember, it doesn't always figure out that you have real labels in the first row. Perfect. Okay, so let me copy this line so I can remember where that is later. There we go. All right, so we've got our data loaded. Let's do a traits CFA. So let me define that model. So I'm going to model equals, and I want to look at what the traits are. So I'm going to copy all this real quick so I can have it on this screen. So my first trait is going to be meaning, and that's going to be defined by MLQ1. So in my data set, it's M1 plus 2 plus 5 plus 10. Okay. And then it's going to be plus song 1 plus song 9 and plus pill 4, sorry, and 17. Okay. And then I'm also going to program in purpose. Okay. And that's going to be M3 plus M4 plus M6, M8, M9, and then song 2, song 8, pill 3, pill 20. All right, so those are just, my traits CFA. Okay. If I also wanted to do, so let's call it something better than model, model.traits. And then let's also do a model for the methods. And this is just doing them separately. And so I'm going to have, deleted the line I needed, the MLQ is defined by the M questions. So every question is going to get used twice. Now let's do these. The song is going to be defined by these 4 S questions. There's more questions than this in the data set, but these are only the ones I'm going to use. Okay. And then the pill is defined by these 4 questions. Okay. Okay. So I've got just a model for traits and a model for methods. All right, what I'm going to do is actually program the rest of the models, and then we'll talk about what they do one at a time and then run them. So I'm going to have all my models definitions first. Okay, so this is going to be model 1. So the first thing you do when you're trying to run an MTMM is program in both methods and traits together. So I'm going to copy these first 2 lines. So really I did this, 1, to make sure it runs and I have all the appropriate questions, which we'll look at here in a second. But 2, also because it helps me make model 1. So model 1 is methods and traits together. But what you want to do is set the cross covariances to 0. Okay. And so we want meaning and purpose to be correlated and then the methods to be correlated, but we don't want the methods and the traits to be correlated. The methods and the traits are related through the fact that they're on the same scale, and so that's actually part of the manifest variables, but we don't want them to cross-correlate. So in lavaan, what you do is you just set them all to 0. You don't want to use orthogonal equals true in the structural equation model line, because that will set everything to 0 and you can't turn them back on, because I tried that. So what you do is you just set the specific ones you want to 0. Okay. So what I want to do is set meanings covariance, so that's a double tilde, to be 0, so 0 times MLQ. I'm going to do the same thing for all of those. So 0 times the song, and the meanings covariance should be 0 times the pill. Okay. So that'll set all of the cross covariances to 0. I've left meaning and purpose correlated because I want to do that. Okay. I'm going to do the same thing here with purpose. So the more traits and methods you have, the more lines you're going to have here. So I have 6 because I'm talking about the cross, so it's 2 times 3. If you have 4 traits and 5 methods, there'll be 20 of these lines. So that's model 1. So model 1 is going to tell us, are our manifest variables measuring the traits, and are they also some of the variance due to the methods? Because you often in a CFA are just examining the traits, but you might have an effect due to the method. So the way you ask the question or the scale that you're using. So this lets me account for some of the variance due to the method's effects by including those as latent variables, which you wouldn't normally do in a traditional CFA. You would normally just test the traits. So for model 2, what we're going to do, let me go back to my Word document, is no traits. So we're going to take the traits out completely and just look at a methods. So it's actually the exact same thing I've already programmed up here for methods. So another reason to write it out. But this is model 2. And so that is a no traits, all methods. And so you want model 2 to be worse than model 1, because if it's only due to methods, then you're not measuring traits, you're just measuring different scales, different wordings of the same scale, essentially. And so you want a model with traits to be better to show that the traits are important, that they're being measured. So this is convergent validity for your traits, showing that the two methods are actually measuring some sort of trait and it's the same type of trait. Okay? Because you want the measures to measure the traits in the same way, but not overlapping. Okay. So let's do model 3 now. Oops. Okay. So model 3 is a perfectly correlated traits and a correlated methods model. So we're going to leave methods in there. And we're going to take the traits and perfectly correlate them. So this is discriminate validity of your traits. So you want your traits to be different things, because otherwise why do you have them as two separate latent variables? So you want the traits to sort of separate out and not be exactly the same. Now, I'm in the social sciences, so we're talking about people here, and so it's often very hard to have completely separate traits. In a perfect world, they'd be totally uncorrelated. But in reality, that never happens when you're dealing with people, and things are always slightly correlated. This is why we like oblique rotations for exploratory factor analysis, is because we let them correlate a little. And so what we're doing in model 3, as compared to model 1, is we're testing if the correlation between traits is 1 or is not 1. So you want that correlation between traits to be low, because that means that they're discriminate from each other. So what you want to do is take model 1. So I'm going to copy model 1 here. And then what we're going to do is just add one line. So I'm going to take my two traits, so meaning and purpose, and I'm going to set that correlation of the traits to be 1, exactly 1. If you just say meaning, purpose with the little tildes, it'll get mad at you because that is already assumed to be there by the fact that they are exogenous variables only. Okay, so that will test if the traits are perfectly correlated. Okay. And then model 4, what we're going to do is test discriminant validity of your methods. So we want the traits to be correlated, not perfectly correlated. We're going back to just regular correlation, let them do whatever they're going to do. And we're going to uncorrelate the methods. And so what that does is it tests if the methods are different from each other. So think about this as a Venn diagram. And here I can kind of draw this in Word probably. See how bad my circle drawings can be. So what you want is traits to overlap some, but not perfectly. And then measures to overlap. If you could get none, that would be great. So let's say this is all of the variance in a latent variable that you're trying to measure. Okay? And that is measured by your indicators, your manifest variables. And so I want to take this method and measure this much variance. Okay, so I've got the method measuring that much of the latent variable's variance. Now if I have another method, I would like to measure basically totally uncorrelated variance. So I can get the most bang for my buck by having two scales that measure very different pieces of the same variance. So I'm still trying to measure that same latent variable, my trait, but I have methods that measure completely different parts of that variable. That would be a perfect thing. If we were talking about multiple regression, these would be uncorrelated predictors, and you could get more R squared because they're not related to each other, so they're not going to suppress each other out. If I instead have almost perfectly correlated methods, what's the point of doing both scales? And so this will let you see if both scales are indeed useful at measuring different pieces of variance. Because otherwise, why are you wasting your time taking both scales and losing degrees of freedom by measuring both of them? Especially if you're going to do this in a multiple regression sort of way. And then you have to think about participant fatigue and cost of the scale if you have to pay for them. So the great thing about MTMM to me is really telling me if these scales are separable, or are they all measuring the same thing? And that is the basic idea of model 4. So we're going to go back to model 1 and copy that, because we just want to edit model 1. But now what we're going to do is set the method's covariances to 0. Okay. And so we're testing if the method's correlations are 0 or not, whereas model 3 is testing if the trait correlation is 1. So we want MLQ is correlated with the song, 0 amounts. And then MLQ, oops, what was that? Oops. Is correlated at 0 with the pill. And then song is correlated 0 with pill. Okay, so that should be all the different ways. So if there are 3 variables, there will be 3 lines. If there are 4 variables, there will be 6 lines. It's very similar to pairwise comparisons in ANOVA. Alright, so that should be good. That's how we would program these models. Now let's take and test our models. Okay. And so my first model I have is labeled, I got model.traits and model.methods. So let's just look at those and make sure they're doing what we would expect. It also will allow us to avoid interpretation confounding if they change a whole lot when we add methods and traits in the same model. If the loadings change just a whole bunch, it might be problematic. Realizing that they are going to change by adding those extra latent variables, because when you add the extra latent variables, the error variance has somewhere else to go. Okay. Alright, so let's do traits.fit is a CFA of model.traits, okay, where we want to tell it what the data is. So the data is equal to data, and then one more thing, just to, because we're going to do this here in a minute, standardize the whole thing. Okay. So traditional MTMM is not standardized on a on a manifest variable. Generally, scaling is you put a 1 on the first loading. Well, what we're going to do for MTMM is standardized on the latent variable, where the variance for a latent variable is set to 1. And that is just the more common way to do it. I've talked about in some of my other videos that if you leave standardization off, you can still get it in the output. But to match what people traditionally do, I would tell you to standardize on the latent variable, because that's going to be what people are used to seeing. Okay. So, so the first thing you should actually do is run all the models you just typed so that it knows where they are. There we go. Do that all the time. So that will be our traits model, and let's run that one. Okay. And it wasn't very happy with us. So it says the covariance matrix of the latent variables is not positive definite. That means the correlation between the latent variables is too high. So let's get a summary and see what happened. So I got traits.fit. Let's get R squared to see if it's a specific variable that's the problem. And then let's do standardized equals true, although that will give us a bit of a repeat. So when I run that, what I can see here, so I'm not going to look at the fit indices for this one Normally you would, but I'm just going to kind of walk through the whole model. My estimates here for the parameters are a bit odd. So they're all significant, but one problem that we might be having is that the meaning scale is like half negative and half positive. And reverse order questions will always give you trouble in specific, like pretty much always actually. And so you might consider rescaling these to be positive. Now, there's no good reason actually why these particular questions should be loading negative, so that's my first bad sign. But I can see that some of them are not very good questions. So standardize all, you want those over to be 0.3, just kind of like EFA. I mean, it's significant at what it's at, but it's not very, it's clear to me it's not a very good question. And then we have some other questions down here that aren't loading very well. And so that's because this example isn't the best, but it runs. And then here's the reason we got the warning. So the correlation between meaning and purpose at the moment is 1.02. And so that is definitely way too high because correlations don't go over 1. When it's really close to 1 like this, that probably means that it's actually close to like 0.95, 98. And structural models aren't perfect, so that's its best guess, and that's usually a bad sign. So what we'll see when we run a model where traits are perfectly correlated, it'll be pretty happy because that's where they're at, is they're almost perfectly correlated. Okay. But we don't have any Haywood cases. All our variances are positive, and then all of our square multiple correlations are less than 1. So that's good, but this is kind of problematic. So in general, I would probably actually stop here and determine if I had specified it correctly, because right now what I'm basically showing is there's no meaning and purpose. In our lab, we jokingly call it MERPUS because it sounds funny, but it seems to me like this should be a 1-factor model and not a 2-factor model. And you wouldn't do a 1-factor model with multitrait-multimethod because that's only one trait. But for the sake of showing you how to do MTMM, I'm going to keep going. Okay. So let's get a picture. So what labels? Let's get the standardized estimates, and then layout. Tree is one of the best layout for these types of models. And once my computer figures it out, this will show me that I've at least, it looks like I've programmed it correctly. So this will give you a visual of, did I do this the right way? You'll see the standardization is up here instead of on one of the questions. So remember the little dash lines means that the scaling has occurred on that variable. Right? And our correlation's too high. All right, let's look at the methods. So I'm going to do CFA of my methods. I'm going to basically cut and paste and do the same thing. Okay. So my methods ran without any problems. Let's make sure there are no problems. Oops. Spelling not my strong suit. All right, so if I scroll up here and look, my questions are still positive and negative on the methods this time. And I've got a non-significant question loading on its methods. And that's not so bad because while its methods all by itself, it probably should load together because these are all on the same scale. But when we combine them together, if everything is being taken up by the traits variance, that's actually okay. And it implies that it's all being thrown into traits and not so much methods. And that's what you'd want, is it to be more methods than traits. Oh, I said that whole thing backwards. Sorry. I do this a lot. You want things, when you put them together and everything moves over to the traits side, that's a good thing for you because that's what you're trying to measure is the traits. And so there's nothing left for the methods sort of variance. And that's okay, because I want to measure the trait really well. I don't care if I'm measuring the scale piece of paper very well. Sorry, I said that backwards. All right. So let's look down here at our variances. Okay, they all look positive. Fantastic. And all of my R-squareds are less than 1, although I have one question that's not being measured at all, essentially. So that's not a great sign. But there are no problems with the model. Okay, so let's look at SemPaths here. So we're going to do the methods fit. Right? And let's zoom in here. Oh, I most definitely don't even know what I just typed. So I typed the summary again. Keep you on your toes here. Let's do wet labels this time. There we go. Try again. This time I should get a picture with some numbers on it. Fantastic. All right. So if I look at the correlations here between my methods, they're pretty high. And that's because they're all measuring the same traits. So what will happen to those correlations is they'll get pulled over to the traits side. We hope, if it's not all methods. So that seems to run okay, which is good. You know, we might have some problems that we can look at, but generally we haven't had too much trouble except for that correlation over 1. And that's because this is kind of the best example I have, where I have multiple measures of the same set of traits. So what we want to do now is test model 1. So let's do model 1 fit. Let's run that as model 1. Okay. And then I'm going to copy this to make my life go a little faster, because it's the same data the entire time. Okay, so model 1 ran and didn't give us any trouble. Let's make sure that's true. Okay, so now in looking at model 1, I'm actually going to cut and paste this into my document because I'm going to use it here in a little bit to do something else with it. But until that point, let's just look at it. So all the questions load. They're loading on, let's look at meaning here. So I got one question that maybe not so hot, which is still our S1 question. But otherwise they seem to be okay. And then on our purpose one, that S2 one is not loading so well. So maybe that song scale is not so good at this. Right? Now if we're looking at them loading on the methods side, it's okay if they're small, because remember we want all the variance to move over to the traits side. So I'm just going to kind of look at those. Cool. We've purposely set the cross covariances to 0, so it's okay that they're 0. And look at how high that correlation is between meaning and purpose. So the correlation is 0.99, and that's why we got that error on the last one, was because the correlation was so high, it's almost essentially perfect, that it didn't kind of know what to do. So it estimated at 102, which is pretty damn close since it's 0.99, and so that's problematic. Okay. Now we've left our traits correlated, and so, methods, and so the MLQ and the song are kind of negatively correlated, but the other ones are uncorrelated, and that's actually good. But my variances are positive, and my square multiple correlations appear to be below 1, so I'd say this model hasn't totally broken. Okay. So let's get the fit measures for this model and write them out in our little table. Okay. So I'm going to come back to my document here. Make this go away and fill in my table. So I've got chi-square and degrees of freedom here. Okay. I've got my, I don't have everything that you need in here, but just the ones to do some comparison here. 970 for my CFI, so that's really good. And then I'm going to come down here to RMC. Oops. And I'm not going to include the confidence interval right now, but if I was writing this up, I would. So it's 049. My SRMR is right here, 034. And I would say overall, this is probably a pretty good model. I mean, there are other things I could look at, but the RMC is in the excellent range, the SRMR is in the excellent range, the CFI is in the excellent range. Okay? My meaning, my purpose scale are way too correlated for this to be divergent traits, but at the moment, model 1's not bad. So let's look at model 2. We can also create a picture of model 1 first, sorry. SemPaths, and I'm just going to copy this line and change out to be model1.fit. Let's make that a little bigger. So now I can see kind of what's happening. So I've got my meaning, questions, all related, my songs. So each one should have 2 arrows going into it, which is going to be kind of hard to see in this view. But you should see that the correlations between the 2 traits over here and the methods over here are 0, which is good. And then there's some little numbers between each one of these. So there's our 0.99. And so I can just kind of make sure I did it right. All right, let's copy this whole thing and change it from model 1 to model 2. Because that's much faster than typing it all again. And so this is why standardized naming is good for you. Okay, so let's look at model 2. Okay, ran without crashing. Let's look at a summary here. So model 2 is where I'm going to set, actually I've already run this model, I'm going to take out the traits. So this is just a methods model. And we looked at this a minute ago and we figured out we had some bad questions. So S1 is not a very good question on any of these models. And then I can look at my covariances here, so you can see how much the correlations change. So they're actually fairly correlated when you don't include the traits, but when you take those traits out, a lot of that correlation disappears. And that's good because that means it's measuring traits and not methods. Okay. Variances are all positive, square multiple correlations are all below 1. So let's look at the fit indices. And that never works. I will one day remember that that is not a thing you can do in the console window. There we go. So let's look at chi-square and degrees of freedom here. So we got more degrees of freedom because we've taken out the traits side, but a much bigger chi-square. My CFI is 0.706, which is not good. And then my RIMC is 0.14, also not good. SRMR is 0.134. Okay. So that's a very big difference in model fit. And we're going to fill this bottom model out once we get all the numbers here. And so the lowered fit indices is actually a good thing for you. So the model itself is bad, but it's a good thing when you're talking about doing the steps for MTMM. Okay, let's look at a picture. So the picture should be of just the methods, and it is. Okay. And then let's copy this whole thing again, do model 3. So model 3 runs and it doesn't crash. Let's look at a summary. So model 3 is where we're going to set the traits to be perfectly correlated. So most of this shouldn't change really. It doesn't. It might change a little bit, but it doesn't change completely. Right, so everything looks okay. And then this meaning and purpose is now not being estimated. It's set to be perfectly 1. So we actually want this model to be bad, but you'll see here in a minute that it's not going to be bad. All of our variances are positive, and all of our R-squareds are less than 1. So let's get fit indices. Try that again. Perfect. So our chi-square and our degrees of freedom right here. And since we only had 2 latent variables for traits, you'll see the degrees of freedom difference from here is only 1. So our CFI is actually perfectly the same. And then our RIMCs, the exact same. Our SRMR is pretty close. And this is actually a good fitting model, which is bad for us. So I said that this is a bad fitting model, and so that's good. This is a good fitting model, and that's bad. Okay, and we'll get into why in here in a second. I'm just going to include all the fit indices first and then get into what is the actual test for MTMM. So let's look at a picture just to make sure we've done everything correctly. Great, great, great. And so meaning and purpose are perfectly correlated, which is not good. All right, last but not least, let's do model 4. Okay. 4 and 4. So model 4 runs. Let's look at a summary of model 4. Okay. And what we see is that the loadings look okay. So we're still doing good. What we've done, however, is, so meaning and purpose are still perfectly correlated, but we've set all of the traits correlations to 0. Sorry, methods correlations to 0. So all these methods are now uncorrelated. Our variances are all the same, are all positive, and our squared multiple correlations are all below 1. So fit-wise, let's see what happened, but summary-wise, it looks like it converged on a reasonable solution. And what we want to do is include our fit indices. Word is doing its crazy thing. Okay. And then let's look here. CFI is 0.950. So that's good. Then RMC is 0.062. So that's good. And RMR is 0.068, and that's also a good fitting model. Okay. And so we want this to be a good fitting, so we can keep going with our steps here. And then this is a good fitting model, which is actually good for us. Okay. So what we're going to do now is talk about the comparisons. So the first thing you want to do, now I don't really recommend a chi-square difference test very often, because it is biased by sample size and it tends to be significant pretty much all the time. But you will see lots of chi-square difference tests in this type of literature, so I'd like to teach it to you. And so to create the chi-square change, we're just going to subtract the difference between the chi-square for model 1 and the chi-square for model 2. Okay, so that's 230 minus 1406. 431. Okay, so it's 1176, and I'm going to do the absolute value. Okay, so that's my change in chi-square. Okay, and I'm going to do that with the same thing with the degrees of freedom. So I got 98 minus 116. Oops. Okay, so that's 18 degrees of freedom difference. Okay. Let's go ahead and do that for all of them. And so what I'm going to do is compare model 1 to model 2, model 1 again to model 3, and model 1 to model 4. So we're comparing everything to what we would consider the perfect model, which is model 1. So minus 231, 156. Okay, so it's 0.75. Okay. And I can do the math on this one. 99 minus 98 is 1. And then the last one, we're going to do 318, 622. The order doesn't matter because it's absolute value. 230, 411. Okay, so 88 to 21. And the difference in the degrees of freedom is 3. So 101 minus 98. Okay, so 3. So 101 here minus 98 here. So what is a critical chi-square? What I'm going to do is open my chi-square table. There we go. Right, and what I want to do, goodness, make it bigger so you can read it, is find 18 degrees of freedom here. and then come across to 0.05. So at 18 degrees of freedom, that's 2887. So our critical number is 2887. 1 degree of freedom is 3.84. I teach introductory stats. So I got that one memorized. So 3.84, and 3 degrees of freedom is 7.82. So I got 3.84, 7.82. So for chi-square, what I'm going to do is the change in chi-square larger than the critical value? If so, it is a significant change. Okay, so is the change in chi-square larger than the critical value? On this one, that's no. Is the change in chi-square greater than the critical value? And on this one, that's yes. Okay. And we'll talk about what do you want to find here in a second. Now, other popular move is to do the change in CFI, and the critical value for that is always 0.01. Okay. So I would just subtract my CFIs. So back to our calculator here. So I got 0.97 minus 0.706. I would tell you to go to 3 decimals since the cutoff score is so small. So 0.264. Okay. And so for CFI, is this number bigger than 0.01? So it's 0.26 bigger than 0.01, so yes. Okay. This is 0 to 3 decimals. So for CFI, I'd say no. And then this one is 0.02. So for this CFI, I would say yes. Okay, because it's bigger than 0.01. So what is the interpretation here? So what do I want to find? Let me put this on a new page so I can type beneath it here. Okay. So for the comparison between Model 1 and Model 2, Model 1 should be better than Model 2. What that implies is convergent validity of the traits, which I can't spell. There we go. And what that means is that what we've done between Model 1 and Model 2 is delete the traits. So if a model with no traits is as good as or better than a model with traits and methods, that's not good for you, because that implies that it is all methods. Okay, so if the methods only model is better than the methods and traits model, that means your traits aren't doing anything and it's all methods. And so you want a model with both to be better. And that implies that your traits are measuring what you think they're measuring. So it's a convergent validity of the trait. So it's saying that the traits are a valid thing. Okay? And so we want a significant change. And you want Model 1 to be better. Okay? And it is. So Model 1 is better. How do I know that? Because it has the smaller chi-square and the larger CFI. Because remember, CFI is reverse scaled. I want it to be close to 1. Chi-square, I want to be close to 0. For Model 1 versus 3, you actually want Model 1 to be better than 3, which is divergent validity of the traits, or discriminant validity. I don't know, it seems to me it always should be convergent and divergent, but discriminant validity of the traits. Okay. And so we want a significant change, because that means that the traits are different things. Okay. So the difference between Model 1 and Model 3 is that Model 3 has a perfect correlation between your traits. And so if Model 3 is better than Model 1 or the same as Model 1, that implies that the traits are perfectly correlated. Now, obviously in this example, the correlation is 0.99, so that's not too hard to see. So this is actually bad for us. We want Model 3 to be a bad fitting model, and it's actually a good fitting model, so that's not so good. And this implies that our traits are not discriminant. Okay, they're not divergent things. And we kind of already knew that. That was a little bit of the purpose of this project, was to show that meaning and purpose were not different things. So it is indeed MRPUS, or a one-factor model. Okay. There are easier ways to test that, but I'm trying to show you MTMM. Okay. So we want actually Model 1 and Model 4 to be equal. Okay. And that is discriminant validity. I think I like divergent better because I can spell that. Discriminant, not so much. has discriminant validity of the methods. Okay, so we want no change. So remember that in Model 4, what we did is we set the covariances between methods to 0. And so we want the methods correlations to be low, implying that the methods don't overlap so much that we can only get away with measuring one of them. So you're trying to show that the methods are actually different things. So they measure different pieces of these traits, and that's good for you because it means the methods are useful. And so we want no change between the methods. And so in this particular example, this is bad because we do see a significant change. So this whole MTMM is a hot mess. But you get the idea where you don't want to change between the methods models because we want the correlations for methods to be kind of low. And again, that implies that the methods all are measuring different pieces of your traits. Okay. So that's how I'd interpret these results. I would have to say that it is really a one-factor model, and that our methods overlap probably more than we'd like. Now, if I had decided, so I did on Model 1 versus Model 2 decide that I have at least convergent validity of the traits, and so, but it doesn't tell me if the traits load better than the methods. So I might have differences between Model 1 and Model 2 that say that traits are necessary. But another important component is that I want traits to be measured better than methods. And so we don't want all of the loadings to be high on methods and low on traits, because that's kind of backwards. You want the questions to load mostly on their trait, and sort of the other variance that's error that you can't normally account for be the method. And so what you do to examine that is you I made this into a table. You can do it however makes sense to you. Compare the loading for the method and the trait to each other. So we're actually, oh yeah, there's a little typo on this table. These two shouldn't be there. We're actually going to add one more line. And we want traits to be better than methods, no matter which way I just said it, because I'm sure I said it backwards again. And what I'm going to do is take my loadings that I pasted a minute ago and use those to measure this. Okay. So it's going to be a bit of fun here to get this table happening. I would either use these all standardized loadings or just the standardized on the latent loadings. You can go either way, just be consistent. So I'm going to use the back side here. So meaning loading on MLQ1, MLQ2. Okay. So I'm just cutting and pasting them into this table so I can compare them against each other. Okay. Apparently I did not turn Do Not Disturb off. So hopefully no one texts me anything goofy. Right. Oop. No, I'm still doing this right. Okay, yeah. We're on our song variables. I am doing them out of order though. Oh no. Okay, so that should be, I just got excited cutting and pasting. These two purpose questions are actually on the bottom. So let's kind of move things around here for a second. Be sure you paste the loadings in the right place. Oops. There we go. Okay, so now I have them all in their loadings for each question. You can also cut and paste the output from R into Excel, and that might make this go a little faster. Okay. So for purpose, I'm going to do the same thing, hopefully in the right order this time. So I've got MLQ. This is the slow part, other than writing all those models. Okay, let's do the right questions. So here's pill. There we go. Okay, so those are all of my loadings. I clearly have some bad questions. So MLQ8 is not doing me very much good, and song 2 is not a very good question for this particular example. And so now what I'm going to do is cut and paste the loadings that are where they're loading onto their traits instead of their methods. Methods instead of their traits. Good gracious. I'm going to look at where MLQ is loading on MLQ, which is methods to methods. I am only human and I say things backwards apparently. Alright, let's do this one. My word is so possessed sometimes. It's a necessary evil in science, right? Dealing with Microsoft Word. There we go. I'm going to do the same thing for the song questions and the pill questions, and then we'll get into why did she go to all this much trouble for a silly table. There, and then 2 more. It's probably faster to type them. Okay. So all that madness aside just now to make this table, what do I want to know out of this table? I want the traits over here to be larger loadings, absolute value, for the methods over here. Because you want it to load more on its trait than its method. Otherwise, you're just measuring because you have this particular scale. Okay? So meaning compared for this question compared to just the fact that it's an MLQ question. So that's yes. Okay, now the very next question is a no. It's measuring the method better than the trait. Okay, the next question is a yes, and then a no. Okay, so half our questions are measuring the fact that it's that particular scale better than they are the trait we are hoping they will measure. The next 2 questions are okay, because this column is greater than this column. The next question is bad, and then okay. I'm going to keep going. So here I'm comparing these 2 to each other. So that's bad. That one's good. That one's good. That one's bad. Good. Bad. Roughly equal, but we'll say yes because it's slightly bigger. That's no. And those are a wash. So if it's a wash, I'd basically say no. I mean, it's yes, but just barely. So what you want here is this to mostly be yes. And there might be a bad question or 2, or questions that just, they load better with their scale than their trait. But really half and half is not good. So you want the traits variance to be more than the methods. Okay, so the loadings on the traits should be higher than the loadings on the methods, or that implies that you can't discriminate between traits and methods. And that's not good. That's saying that there's no convergent validity for your traits. Okay? And so that answers the question for Model 1 versus Model 2. Yeah, Model 1 is better, but it's not better in a good way. It's just better because we have extra variables. It's not better because I'm measuring the traits better. Okay. Let's look at the correlation between meaning and purpose. Okay, so that's 0.99 here. And so you might, if you had more traits, there'd be more boxes here. And you want the traits correlations to be really low. That's Model 1 versus Model 3. And yeah, it's not. So this is still bad, just like this comparison up here said that Model 1 versus Model 3 wasn't what we wanted. There's no difference between the models, but we wanted a difference. And let's lastly do methods correlations. So that's here. So I got MLQ to song, which is negative 0.54. Pill to MLQ, 1.6. And then pill to song, 0.046. Okay. All right. lastly, we want our methods correlations to be low, which implies that the methods are measuring different pieces of each trait. And so the MOQ in the song here correlation is not low enough. Okay. The pill with everything else seems to be pretty low, which is good. That means it is divergent, is different from or discriminate from your other pieces. The MLQ and the song may not be discriminant enough from each other to include them together. Okay. And that is why Model 1 versus Model 4 found a significant difference, because 0.545 is significantly different from 0. And so that's why when we wanted no change, we still found one. Okay, so Model 3 and 4 are not showing us what we would like to see, and you can see that by looking at the traits correlations are too high, they're too close to 1, and the methods correlations are not close enough to 0, aka they're larger than 0. And so that does not give us discriminant validity of our methods. Okay. All that together is a MTMM, very traditional MTMM. Like I said, if your first model won't run, you can get a Haywood case, which generally amounts to a negative variance in these types of models. I would tell you to try correlated uniqueness as one of your types of models, or to look into some of the handbooks on MTMM, which explain even more different types of MTMM that you can try if this is your goal to test this sort of convergent and divergent validity.